This is Mr. Sitta. Going to go over intermolecular forces, the worksheet. I'm going to redo this. I'm going to go through number 1 through 23. Okay. The first problem asks about crystalline solids. The one thing you have to know about crystalline solids is they have a highly ordered structure. It's a regular repeating structure. That's what you're looking for crystalline solids. Amorphous is without shape, and amorphous would be without structure. Okay, random. In liquids, the attractive intermolecular forces are, okay, there's a few choices that are true. They're strong enough to keep the molecules relatively close together, but they're not strong enough to keep them from moving past each other. Okay, put those two together and you get E. They're strong enough to hold the molecules relatively close together, but not strong enough to keep them from moving past each other. Okay. Number 3, as a solid element melts, okay, the atoms become more separated, not closer, and they have less attraction, and that's why, because they have less attraction, that's why you go from a solid to a liquid or a liquid to a gas. Okay, well, this is asking melting. Okay, number 4, when I posted this on the test, I gave you all the structures of these, and without having the structures, you really can't answer this question. It asks which one exhibits dipole, so I'm looking for something that's polar. Okay, polar means that your electrons are going to be unevenly distributed. If I look at the structure for xenon tetrafluoride, you have xenon connected to 4 fluorines, and then you have a pair of electrons up top and a pair on the bottom. Well, they're symmetrical, so there's no unevenness. So this would be xenon tetrafluoride as drawn would be a nonpolar molecule. Okay, chlorine did it up here. Chlorine is just 2 chlorines. Anytime you see a diatomic, they're nonpolar. And anything that's nonpolar, like XCF4 or Cl2, that would be LDF, London dispersion forces, is the only force when you're nonpolar. Okay. Carbon dioxide is a carbon with an oxygen on one side and an oxygen on another. Again, this is symmetrical, so there's no unevenness to the distribution of electrons. Interestingly, carbon, because it has a double bond O, if you put it in water, carbon dioxide, the oxygen can hydrogen bond to the OH in water. And that's why carbon dioxide tends to be soluble in water, and you can make something like seltzer water or carbonated beverages. But by itself, it doesn't have any hydrogen bonding, so that this is nonpolar. I might say, if I did have a carbon with 1 oxygen, that bond is polar due to the difference in electronegativity. But when I have both, it creates a vectored force that pulls either way, and they cancel each other out to become nonpolar. Okay. BCl3, I drew that up here. You have 3 things pulling in 3 different directions, and again, each bond is polar, but you put them all together and the vectored forces cancel each other out, so BCA3 is nonpolar. There's no unevenness to the distribution of the electrons. When I go and look at the structure for arsenic trihydride, okay, you have 4 different poles, one going up, this is called a tetrahedral, one going over, one going back, one coming out. The 3 hydrogens, actually the arsenic would be pulling the electrons away from the 3 hydrogens, making each hydrogen a little bit positive. Well, there's only one pair of electrons up top, which would be a little bit negative. So this side of the molecule would be negative, and this side would be polar. The electrons are not distributed evenly, so arsenic trihydride is the dipole you're looking for. Okay, number 5, 2 things that determine whether something has a dipole is the molecular mass. Now, if you have something that's all nonpolar, the one with the highest molecular mass would have the most electrons, would be the most polarizable. Well, in this case, they give you data for a dipole moment. That's the ability to be polar. That's the polarization of it. Really, all you have to look at is the dipole moment. Acetonitrile is carrying a dipole moment of 3.9, so that would be the biggest dipole of all these. The molar masses, they're all similar, and if you look at the 50, it's not creating enough of a dipole moment. Okay, it really depends on the dipole moment in this. And again, if I draw this molecule out, I have electrons being drawn towards a nitrogen because the whole thing is nitrogen's electronegative. So this side is very negative. That tends to pull all the electrons towards this side of the molecule. So the other side would be a little bit positive, and that's your definition of a dipole. Okay. Number 6. Okay. This chapter is mainly on intermolecular forces. So if I have something like sodium, sodium's ionic. And it does talk about solids, liquids, and gases. So if you have purely ionic compounds, they form crystalline solids, regular repeating structures. But if you put an ionic compound, sodium, with something like water, well, water is hydrogen bonding, but hydrogen bonding is extreme dipole. Okay, so a hydrogen bond is like a dipole to the extreme. Well, what you have is an ionic compound with a dipole, and they have a natural attraction. This is why salts dissolve in water. Okay, water is highly polar. Both the hydrogens would be positive, the oxygen would be negative. The Na, the +1, would tend to be surrounding by all the oxygens of water to be hydrated. But this is an ion dipole force. Okay, it's not really an intermolecular force. It's a force between ions and dipoles. So it's between ions and molecules, D. But it's an important force. Okay, the strength of London dispersion forces in between like molecules depends on your molar mass, and it's not the mass that's important, it's the number of electrons. So every time we say molar mass, I don't like saying that, because it's really the number of electrons that makes it polarizable. So there's your answer: molar mass and polarizability. Vapor pressure is a property, size has nothing to do with it, not volatility is a property, not size. A. Now, this is just a definition. The ease with your charge distribution on a molecule can be distorted by an external electronics field. That's called polarizability. And in London dispersion forces, you see polarizability because there's an adjacent molecule. If it's nonpolar, even if it's nonpolar, the electrons can pull themselves to one side, and that would make this side a little bit positive. Well, that would induce a dipole on the adjacent molecule, and that creates an attractive force. These electrons can come back to the other side, make that negative. Well, that would repel the electrons. They'd go back here, and then it would go back to being negative. And this goes just back and forth, but overall there becomes a net charge between the two molecules. That's the definition of London dispersion forces. So the answer to 8 is polarizability. Okay, which one has the highest boiling point? Okay, all these are based on C2H6. So C2H6 would be ethane. Okay, hydrocarbons are nonpolar, and if I replace all these hydrogens with like iodines, all these are going to be nonpolar, so their force is LDF. And in this case, molar mass comes into play. The one that's the most has the highest boiling point would have the strongest force. So you're looking for the thing that's the heaviest, and it would be iodine. So the answer is C2H6. Because it has the most electrons, that makes it the most polarizable. The strongest force is the highest boiling point. Well, that corresponds to the lowest vapor pressure. Okay. What is the predominant intermolecular force in CBr4? These BR4s are all pulling in equal directions, so they all cancel each other out. So that would be nonpolar. Anytime you see a hydrocarbon saturated with hydrogens or any type of halide, they're going to be nonpolar. Okay, and if it's nonpolar, then we're looking at London dispersion forces. If I was to replace any of the bromines with a hydrogen, so if I suddenly put a hydrogen here, that would create a unevenness in its electrical distribution in the electrons. The hydrogen would tend to get the electrons pulled away from it, and this side where the hydrogen would be positive. So one way you can make a polar molecule is by having two elements of unequal electronegativity. Okay, they're pulling unevenly, but this is all even. Okay, I might mention one thing since you're talking about vectored forces. The structure of water has a bend in it. If it didn't have that bend, water would be nonpolar because the vectored forces would cancel each other out. But the bend is what keeps the oxygen negative and the hydrogens positive. The bend in the water, the shape, is what puts the polarity in it, is what makes water have a extreme dipole, hydrogen bonding. Okay, hydrogen bonding, special case of dipole-dipole interaction. It's especially strong. Now, if you're comparing hydrogen bonding is always hydrogen. Okay, the reason hydrogen is important is it's only surrounded by one electron. When that electron gets pulled away by something highly electronegative, the nucleus is then exposed. And hydrogen is the only element where you can expose a nucleus and see the positive charge. So that creates an extreme dipole by having a nucleus exposed. The electrons get pulled away. To pull it away, you need to pull that away, what you need to have is extremely electronegative atoms. And if I look at my periodic table, electronegativity increases as you go up, and this all goes back to Coulomb's law. As size decreases, your attractive force increases. So things that are high on the table up tend to be electronegative. Things to the right tend to be electronegative because of the effective nuclear charge. It's the extra protons that are pulling your valence electrons, your outer electrons. So this would have +1, +2, +3, 4, 5, 6, 7, 8. Now we don't consider noble gases. We don't consider them because they're not going to gain any electrons because their shell is full. And since they have a high Z effective, they're not going to lose any, and that's why noble gases tend to be non-reactive. The most electronegative element on the table is fluorine. The reason is its Z effective is a +7, and it's very small. The least electronegative would be the largest, would be to the left. That's the least Z effective, a +1. Only one extra proton pulling the extra electron, and all the way down. So you would look at not really fluorine, but cesium, because fluorine is highly radioactive and hardly any atoms at one time of fluorine in it exist, and only for a moment they exist, of francium. So cesium's the least electronegative, that would be a 0.7, and fluorine is a 3.3 as a 4.0. So the difference between that is 3.3. That's your most extreme electronegativity. If you put cesium with fluoride, they don't share electrons. The electrons transfer from the cesium to the fluorine, so that makes it an ionic compound. And that's why in general we say if you put a metal with a non-metal, generally ionic compounds. Not totally true. If you have like aluminum with oxygen, the difference in electronegativity is not that great. So sometimes when they're close together, they can make, they're actually covalent compounds. Tin would be covalent with a lot of nonmetals because there's not a big difference. Okay, tin, lead, anything that's close to the Zinno line. Okay, let's see. The one thing I wanted to point out is that your three elements that are capable of making hydrogen form hydrogen bonding are the top right, N, O, and F. The strongest one is F, then oxygen, then N. Okay? All right. So when it comes to hydrogen bonding, HF is the strongest, then water, OH, then NH. You can put them in order of strength. Okay. Number 12, we're looking for hydrogen bonding, and I'm not sure these are the same examples that I used on the online test. Similar. This one does not have hydrogen bonding. I'm looking for the H to be directly connected to the O, so the answer is no. The F would have to be directly connected to the H, so this is a no. Here's an H and H, but they're not directly connected to the O, so this is a no. Here's your hydrogen bonding. The H has to be directly connected to the N. Hey. The H's and F's here are not directly connected, so only D is hydrogen bonding. This one will not have hydrogen bonding. Again, I might have used different examples on the online test, but the idea is the same. For hydrogen bonding, I'm looking for HN, OH, and HF. So this one, there's no hydrogen bonding, so that's your answer. B, there's your HO, that's hydrogen bonding. C, there's your HO, that's hydrogen bonding. And D, NH, that's your hydrogen bonding. If you ask me which of these had the most hydrogen bonding, well, I would eliminate the N because that's the least, that's not as electronegative as the O. And since this one has two OHs, I'd say probably peroxides, this is hydrogen peroxide, would have more hydrogen bonding than just ethanol. Okay. All right. Which one has the highest boiling point? For the highest boiling point, I'm looking for the most bonding. So if I look at the CH4 is nonpolar, CO2 is nonpolar, and just an atom is nonpolar. So I'm going to eliminate A, B, and D. B, C, and D. Ammonia, NH3, has hydrogen bonding, and so does water. Which one has the strongest hydrogen bonding? That would be the oxygen is stronger than that. And so the answer is A. Okay. All right. I can't see the answer to this one. This one is asking which one is got the strongest force, or whatever property would be strongest. These are all LDF. They're all these are diatomic molecules. Okay. The one that's heaviest has the most force, so the one we're looking for is bromine, because bromine has more electrons than all the rest. So the answer is B. Okay. In which of the following molecules is hydrogen bonding likely to be the most significant intermolecular force? Okay. I'm going to get rid of CO2 because it's nonpolar. I'm going to get rid of CH4 because it's nonpolar. This would be LDF. This would be LDF. Now, right here I have OH, NH, and OH. These are all hydrogen bonding. But I'm going to eliminate, firstly, the ammonia because that's weaker than hydroxide. And then the only difference between these two are the chain length. In methanol, it's very short, so that creates more of a polarity if you're short. As this chain length increases, this becomes more like an LDF molecule Okay, uh, the polarization of it decreases. It's not as thing. So I want the one with the shortest chain of carbons. So the answer would be D and not B. Okay. I'm going to ask you this question a lot, so look for it on the test. If you have carbon and hydrogen, that's a hydrocarbon. Hydrocarbons are always LDF. Okay, there's no polarity there. So you're looking for London dispersion forces. You would think that's the weakest force. Well, if I had just CH4, okay, it's a very short chain, and this would be methane gas. The fact that that's a gas, okay, means it's a very low force. Well, that would be lower than water. So if I had H2O with hydrogen bonding, that would make water a liquid. Well, when it comes to LDF, it can actually build up. So in something like this, where I have 12 carbons, okay, the LDF can actually be greater than hydrogen bonding. Suddenly you have a large surface area, and this can be highly polarized. So as the chain increases, the polarization of it increases, and that can actually effectively be greater than water, because as this gets greater and greater, it would become a liquid, an oil-like liquid, like diesel fuel, then motor oil, and then like heavy-duty like grease lubrication, and finally like if you get to like C26, you're looking at like Vaseline petroleum jelly. And if you get even higher than that, it would be like asphalt, and that would effectively be higher than water because the LDF is increasing on it. One other thing I'll mention about petroleum, if this was highly branched, like in a circular where all the C's were branched, and this became like round, well, if the two round molecules would only be touching right there, so a minimal surface area for a hydrocarbon is less force than a large surface area. And this is how you refine gasoline. Gasoline is usually C5H12, like that would be pentane, up till maybe like C10H22 mixture. Okay, if you take gasoline and have it in a straight chain, then you have a lot of force between the molecules, so you get a very low vapor pressure. Okay, that doesn't burn well because it's not more like a gas. If you branch it, okay, that burns very well. That's what we call octane. Okay, we normally think of octane as being CH8, 18. Well, octane doesn't refer to the amount of carbons. Octane refers to the amount of branching. And so if you want a higher grade of gasoline, when they refine it, they make it branched, and that burns better, gives you more energy. If you burn a car with straight run like C5H12, the engine will knock. Actually ends up putting a hole in the cylinder. It doesn't run well. And when you put it with a very low vapor pressure, it burns well. Okay. The next one, the energy required to expand the surface area of a liquid.